Okay, for our final talk of the day, we have Jonas Frey talking about composable monadic GAT extensions.
Thank you. Yeah, okay. As the title said, monadic extensions of generalized algebraic theories. So I want to start by quickly recalling what a generalized algebraic theory is. So generalized algebraic theories, probably everybody knows it already, but it's like combining algebra and type dependency. And the most famous generalized algebraic theory is the generalized algebraic theory of categories. And so that has, we have a sort of objects. So I'm going to say sort, not type. And so we have morphisms. So the sorts of morphisms are presented as dependent in two variables on the objects. And this way we can write the type of composition appropriately. And as you all know, we cannot present categories as an ordinary algebraic theory. The other solution would be to do a partial composition as it is done in essentially algebraic theory, but today we're talking about generalized algebraic theories. And then, yeah, so we have composition, identity, and then some axioms. And here's another example, and that's the theory of graphs. And that's basically just the sort signature of the theory of categories. And so this is a subtheory of this one, and conversely, this one is an extension of that one. And so today I want to talk about extensions of theories. That's why I have these two examples. Okay, and so in full generality, generalized algebraic theories, well, are always given by ordered lists of axioms that somehow look like that. The axioms always have a context. And then on the right of the turnstile, we have declarations of sorts or operations and term and sort equations. And yeah, no sort equations in these examples, and it's not clear if we ever need them actually. So at least it's not clear if we need them in the axioms. We always need sort equations that we obtain by substitution instances when we substitute different terms for the parameters of a dependent sort. Okay, so for any generalized algebraic theory, we have a syntactic category, and that's also known as the category of contexts. Well, because the objects are contexts, so lists of variable declarations, and the morphisms are substitutions. And I give two examples here. So if here we have a substitution from this context with 5 variables to this context with 3 variables, where, well, here we have, in the context, we have 2 composable morphism variables. So we are still in the theory of categories. And we compose them, and then we only need 2 object variables because we don't need the y anymore, because in the type of the composition, the y doesn't appear anymore. And here's another example of a morphism with the same domain. And here the difference is that we only have variables, and 3 different variables in the substitution, and that's a projection. And so projections are a special class, and so they turn the syntactic category into a clan. Or rather into almost a clan. So what is a clan? We've already seen in the previous talk, but I'm going to recall it. a clan is a small category with a terminal object and a class of arrows that I'm going to call display maps. We can also call them vibrations. And these are supposed to be closed under composition, contain terminal projections, and pullbacks of display maps along arbitrary maps exist, and are again display maps. And well, the syntactic category of a generalized algebraic theory is a clan, but so strictly speaking, taking the projections is not enough because we want the display maps to be closed under isos, and we just close under isomorphisms. And so what is it good for? Well, the clan structure on the syntactic category gives us a very direct way to define the models of a generalized algebraic theory. And so the model, a model of a clan is a functor to Z that preserves the terminal objects and pullbacks of display maps. And so if the clan is given by as a syntactic category of a generalized algebraic theory, then this is going to be a model of this theory. And up to equivalence, by the way, every clan is the syntactic category of a generalized algebraic theory. Okay, and we write mod for the category of models. So what we are interested in today is the functoriality of this construction of categories of models. And to tell you how this is functorial, I first have to tell you what a clan morphism is. So a clan morphism is just a functor phi from one clan into another, which preserves the terminal object, display maps, and pullbacks of display maps. And if I have a clan morphism, then I get a precomposition functor between covariant Z-valued functors categories here, and that restricts to a functor between the categories of models viewed as full subcategories of these functor categories. And so in this diagram, both the phi star and the phi upper bullet have left adjoints that I have, and here I did it the wrong way around. I want the phi bullet on the top. And so, but the subtle point is that the left adjoint of the forgetful functor between algebras or between models need not be the restriction of the left adjoint between the category between the the precomposition functor between the Z-valued functor category. And so Sina mentioned calculus of mates or exact squares. This means that this square is not exact in two-category terminology. Okay, so, and what I want to talk about is so this adjunction given by the phi lower bullet and the phi upper bullet. So the phi lower bullet should be here. When this is monadic, meaning when the models of T are equivalent to the algebras for the monads obtained by composing phi upper bullet and phi lower bullet. And so this monadicity is very well understood for ordinary algebraic theories, single-sorted or many-sorted, and I'm going to quickly discuss that. So a single-sorted algebraic theory is also known as algebraic theory or Leuven theory, Leuven theories are the syntactic categories probably. So, but these are theories that we can understand as specific generalized algebraic theories, and it's those with a single base sort and no dependency, and then only operations and equations. And such theories can always be viewed as extensions of the theory with only one sort. And here the induced adjunction is always monadic. And this is the well-known fact that single-sorted algebraic theories correspond to finitary monads on set. And that also works for many sorted algebraic theories. So if we have an algebraic theory with a set of sorts I, then the models will always be monadic over set to the I. And so one thing that is slightly less well known, and I also only learned like half a year ago, I think, is that by a simple cancellation property, arbitrary extensions of single-sorted algebraic theories are monadic. So here, for example, I have the theory of monoids, and here I add a commutativity axiom, so that's an extension by a new axiom, and that's monadic. And another example is rings over abelian groups. And why is that? That's simply by this cancellation property. If we have two composable functors where the second one is monadic and the first one has a left adjoint and the composite is also monadic, then the first functor is also monadic. So, and that means that arbitrary maps or extensions of algebraic theories are monadic, and the same works for in the many sorted case. The only thing that is not monadic is adding additional sort symbols. That's never going to be monadic. Okay, so what happens with generalized algebraic theories? So there are two obstructions here, or let's say, well, it is a well-known fact that composing monadic functors is a bit subtle. In general, monadic functors need not compose. And I'm going to present two instances of that phenomenon with an interpretation in terms of a syntactic interpretation or explanation in terms of GATs to kind of shed some light on this phenomenon. So here is a first example. We know that small categories are monadic over graphs, and graphs are monadic over set square. So we have a forgetful functor from graphs to set square, which sends a graph to the pair of the set of vertices and the set of edges. But the composite is not monadic. So one way to understand what is going wrong is that, well, if we think about this extension, or if we think about this forgetful functor as corresponding to an extension of theory, then set square is the theory with two sorts, no operations, and then to go to graphs, we add two operations, namely source and target. On the other hand, if we want to view the theory of categories as an extension of the theory of graphs, then we have to take the theory of graphs with a dependent sort of arrows or edges. And, well, these two theories have the same models, but they are not the same. And that's kind of one way of understanding what's going wrong, why something is wrong with why the composite is not monadic. But it turns out that, well, here is another example where we have, like, we don't have a mismatch in the middle, and still there's a failure of monadicity of the composite. And so what happens here is that I start with a theory with two base sorts, one dependent sort. Then I extend it by a constant, and then I extend it by an operation whose context, where the context appears, the constant appears in the context. And so basically we are creating a new substitution instance of this dependent type C by introducing a new constant. And so then composing these two, we also get something that is not monadic. And that's kind of the general problem with composing monadic extensions, is that we get these new substitution instances of dependent sorts, and they can cause problems. So, okay, so in the following, I want to present a class of monadic clan extensions that do compose, and basically by avoiding this kind of phenomenon. At least that's my interpretation. The criterion I'm giving is purely category theoretic. So, well, and here it is, that's the criterion. A clan morphism, phi from S to T, is monadic whenever the forgetful functor between models is conservative and reflects algebras in the sense that this square that we saw earlier already is a pullback or a bi-pullback. And it doesn't matter if you say bi or not, because the vertical maps are isofibrations. So strict pullbacks are automatically pseudo pullbacks and bi-pullbacks. And so the proof is pretty easy using Beck's theorem, and I'm not gonna spell it out now, but I want to instead quickly mention a few examples. So the extension where we go from the theory of graphs to the theory of categories that we had at the beginning, so that fulfills the criterion, and that's basically because adding the operations in the theory of categories doesn't add any new substitution instances of sorts, because, well, there are no operations whose codomain is the sort of objects, and the only dependency is on objects. On the other hand, so this is the first factor of this non-composable sequence of monadic extensions. So that's a monadic extension, but it does not fulfill the criterion. And so I think if we go from the theory of two categories over the theory of two graphs, I thought it's a counterexample, but now I'm not sure anymore. So I'm not going to say anything about that. Instead, I want to mention monads with arities. So it turns out that this criterion, that this square is a pullback, is very similar to something that comes up in the context with monads with arities. So a monad with arities is a monad on some category X, together with a small full subcategory of X. And, well, we say this subcategory is an arity for the monad if for every object X, the canonical colimit that presents X as a colimit of objects from C is preserved by not only by T, but by T followed by the nerve embedding into the presheaf categories, into the presheaf category. And now there's this theorem that says if C is an arity for a monad, then we have a bi-pullback where the category of algebras for the monad is somehow given by a bi-pullback. And on the top and the bottom line, we have presheaf categories. And it's, yeah. So this theorem is due to Berger, Melius, and Weber in this paper about monads with arities. And so it's really very close. So here we have covariant functor categories in the bottom. Here we have presheaf categories, but that's just convention. Which way around you take your, yes? Yes, I meant to write dense. Apparently, I forgot the word dense. Very observant, thank you. Yes, it has to be dense. Otherwise, this need not be a colimit. Yes. Yeah. So, and quickly, so one major like intuition about this density theorem is that you recover the Siegel condition if you take X to be the category of graphs and you take the dense small full subcategory to be the graphs that are like finite non-empty chains of this form. And then we get in this diagram, well, on the bottom left, we get some relative Kleisli category, and that's gonna be precisely the simplex category. And I should have written delta here. And so we get something very similar if we take the Clan morphism corresponding to this extension of generalized algebraic theories. But now these index categories of the diagram categories are a bit bigger. So here, for example, we do not only have these finite chains, but we have arbitrary finite graphs. Okay, that's it. Thanks for your attention.
Do we have any questions?
Thanks. Can you go back to failure number 1?
At the beginning?
Yeah. Yes. No. Okay. So you had two failures, right? 2 failures of compositionality.
Failure of composition,
Yes.
compositionality.
And you had 2 of them, right?
Yeah. Yeah, here. This one.
Okay, right. So you mostly talked about the second one.
Yes.
So here I just wondered if you could say a little bit more. So these are really presenting the same thing, but in a different presentation, right?
These 2 theories, yeah.
Yeah.
So these are 2 different presentations, or like 2 different theories which have the same category of models.
Okay, so then is this failure just due to the fact that, I mean, we have, in some sense, the wrong notion of what it means to be the same? Or is that a strange interpretation of this?
That you mean, so I don't know if you've seen me talk about clans before, because I've given talks about duality for clans in the past, which is is about this point that different GATs or clans have the same category of models, but this category of models can be equipped with additional structure in the term of a weak factorization system, and that exhibits the difference then. And I would not say that we get the wrong notion of models. It's because, the factorization system has some kind of information of what it means to be a free extension of a model, and yeah, I don't know if that answers your question.
Yeah, it kind of does. Thank you.
Do we have any more? I'll have a quick one. Is it possible to run any of this backwards, in the sense that if you know that a morphism is monadic, that there has to be some nice description of it as an extension with certain properties?
That's a good question. So in general, if we have a well-behaved, we might ask that if we have a well-behaved extension of this form, and maybe S is given by a syntactic theory, can we get T by a theory that is only extended by operations and equations? And I think yes, but I'm not sure.
All right, let's thank Jonas again. And that's it for today.